Hi everyone, and welcome to the Chapter 9 lecture for Chem 100. This chapter is all about acids and bases and buffers, which are things that help us to balance out acids and bases. In fact, balance is kind of a theme in this chapter. So this is probably one of my favorite chemistry memes. It's also a good mnemonic for remembering the pH scale, and it is you're a 10, maybe on the pH scale because you basic. My little attitude snaps, okay? So the higher the pH, the more basic it is, which is something that students sometimes get confused between acids and bases. All right, let's get started. So acids and bases. Acids tend to have these properties. They tend to be sour tasting, so you find a lot of citric acid in citrus fruits, which make them very acidic, so things like lemons and oranges and limes. Also, soda contains carbonic acid. Any carbonated beverage contains dissolved carbon dioxide, which reacts with water to form carbonic acid. So that's why they're not great. These acidic things are not great for your teeth because acids, as we'll see, can be very corrosive. Bases tend to have a bitter taste. So there's not a lot of bases in our diet. In fact, a lot of poisons and toxins are basic, and so they have that bitter taste, and that bitter taste was really an adaptation to steer us away from eating things that are poisonous. So you don't find a lot of bases in foods, but you do find them in a lot of cleaning products because bases tend to have a sort of slippery feel. So liquid plumber, which is like, or Drano, which helps you to clear your drain. Strong bases are very caustic. They erode things, so they help to break up clogs, but they also are slippery and help them slide. Soap. All soaps are made from a reaction with a base and a fat. If you've ever made homemade soap, you can do that. You just need a base and a fat. And so soaps can tend to, usually soaps are pH balanced when you buy them. So they're hopefully not too basic, but they're usually on the basic side, but that's also the base is what gives soap that slippery property. So acids and bases, those are just some of their properties, but what is their chemical definition? So there's a couple of different definitions. The first sort of most elementary definition, and the first one that was coined, was the Arrhenius definition. And according to Arrhenius, acids are things that produce hydrogen ions in water. Hydrogen ions are H+. FYI, we also call these protons. Protons is another way to refer to hydrogen ions. Because if you think of what is a hydrogen ion, it's a hydrogen atom, which is one proton and one electron, and it has lost one electron. So all that's left is a proton. So a hydrogen ion is the same thing as a free proton. All right, so a classic example here is hydrochloric acid, HCl. So hydrochloric acid, when you put it in water, you dissolve it in water, it dissociates fully into hydrogen ions and chloride ions. So it produces hydrogen ions in water. So when you see H+, free hydrogen ions, that should clue you in we're talking about an acid. That would be an acidic solution. Technically, hydrogen ions don't actually float around on their own in water. In water, they tend to hitch on or piggyback onto water molecules. So here's a water molecule, and here's a free proton, an H+ ion. And what it does is actually will become part of this water molecule, and it becomes a hydronium ion, H3O+. So hydronium ion is H3O+. And so when you see H+ or H3O+, hydronium and hydrogen ions are kind of synonymous in acid-base chemistry. So sometimes you'll see it written as H+, sometimes you'll see it written as H3O+. My cat just fell. Bases are things that produce hydroxide ions, OH minus ions, when you add them to water. So sodium hydroxide is a base. It's actually the base that's in Drano. And when you put it in water, it breaks up into sodium ions and hydroxide ions. These hydroxide ions are what make it basic, a basic solution. So that is a very simple explanation of what acids and bases are, and it depends on them being dissolved in water, but sometimes we need a broader definition of acids and bases. So the more widely used definition of acids and bases in chemistry is the Bronsted-Lowry definition. And these two reactions that I have examples of here happen to include water. But it's a slightly broader definition. So in this one it says that acids are proton donors. So they give up a proton, an H+. So here's that same example of hydrochloric acid. All right, so this is the Cl and the H, and here's a water molecule. And the HCl is giving up a hydrogen. It's going onto the water molecule, so it becomes a hydronium ion. And then we have a free chloride ion. Bases, conversely, are proton acceptors. So they are things that gain an H+ in a chemical reaction. So for example, we have NH3 ammonia, and it reacts with water and it becomes ammonium, the ammonium ion here, NH4+. So it gained one H and one plus charge, gained a proton, and in this case the water was the one that lost the hydrogen, that lost the H+. So you can note in these two reactions we used water as a reactant in both of them, right? But in the first one the hydrochloric acid acted as an acid and the water was the one that acted as a base. It was the one that accepted or gained an H+. In the second reaction, water acted as an acid. It was the one that was the proton donor. It gave the H+. So the Bronsted-Lowry definition is that acids and bases are sort of codependent, that when one molecule acts as the acid, the other acts as a base, kind of like redox reactions, where one thing loses electrons and the other gains electrons. So acid-base chemistry is kind of similar to redox chemistry, except what's being transferred is not electrons, it's protons. So they're very similar. All right, so let's just do a quick sample problem where we are identifying whether a reactant is an acid or a base. And we're remembering that an acid is defined as a proton donor. It gives a proton, and a base is a proton acceptor. It receives one. So we're looking over the course of the reaction, who's the giver and who's the receiver. So in this first one, we've got HBr and H2O. Well, first, just looking at them, they both have hydrogen as part of their formula. So technically either one of them could be an acid because they both have a hydrogen to potentially give. We look at what they come on the flip side. All right, H2O becomes H3O+. So it gained a hydrogen. It gained an H+. Sorry if you can hear that car alarm going off outside. And the HBr, conversely, becomes Br-. So it lost an H+ over the course of this reaction. All right, so it lost one. That means it was a donor. It gave it away. So the HBr is our acid because it was the proton donor. And in this case, the water is our base because it was the proton acceptor. It gained a hydrogen. All right, and let's now do the second one. So we've got H2O and we've got the cyanide ion. So just looking at this, I can tell you already which one is going to be the acid, because an acid is a proton donor. It has to have a hydrogen, an H plus, that it can give. And the only one that has hydrogen is the water. So I know this one's going to act as the acid, but let's just to prove it, let's look at what it becomes. H2O becomes OH minus. All right, so it does indeed lose an H plus, a proton. So this one is our acid, and the cyanide ion does in fact gain an H plus to become hydrogen cyanide, and this is our base because it accepted or it received that proton. Right? Notice in these two examples, it's purely coincidental that the first compound is the acid and the second is the base. All right, it's not always going to be that way. It's not always acid plus base. Sometimes it's base plus acid. It's purely coincidental that it just happens to be in this order, just so you know. It's not always written in that order. So acids and bases, just like electrolytes, we saw that electrolytes are things that dissolve in solution to form ions. All right, acids and bases are electrolytes. They form ions. Protons, H plus ions, and hydroxide ions are ions. So they are electrolytes. And so just like we have strong and weak electrolytes, we have strong and weak acids. So strong acids are ones that completely dissociate, completely being the key word for strong ions, or for strong acids and strong electrolytes. They completely dissociate, so they have that one-way arrow, and they will completely, so all of the HCl will dissociate into hydronium ions and chloride ions. Same thing with strong bases. They will completely dissociate. So sodium hydroxide is a strong base. It completely dissociates into sodium ions and hydroxide ions. Weak acids and bases only partially dissociate. And by partially, we mean really a very small percent, like usually less than 5% dissociation. So this guy right here, this is acetic acid, which is in vinegar, will only partially dissociate. So remember, with weak electrolytes, we have that partial dissociation, showing that double arrow. This is a reversible reaction. And it will dissociate by spitting off a proton, and then the rest of the molecule, where that proton left, there's a negative charge. All right, so that OH groups just becomes an O minus. So this should be familiar because this was the same molecule we looked at when we talked about weak electrolytes. We said the only weak electrolytes that you need to know are carboxylic acids, COOH functional group. Those carboxylic acids are weak electrolytes. They're also weak acids. All right, well, I guess I'll just say one more thing. So I think there's 6 strong acids and 6 strong bases, and you don't need to know them or memorize them for this class. If you're given a problem, it will state whether it's a strong acid or a weak acid. But just so you know, strong acids and strong bases are relatively rare in nature. Most acids and bases are of the weak variety, are weak acids and weak bases, especially in biology, biological systems. We do have strong acids in our body. In your stomach uses strong acid to help unfold proteins and prepare them for digestion. Also helps to sterilize your food to kill any bacteria or viruses that you may have consumed. But most of the other acids and bases in the body are weak acids and bases, because strong acids and bases are also often very caustic and damaging, like Drano. The neat thing, though, about acids and bases is that they neutralize each other. So when you have a strong acid and you mix it with a strong base, you end up forming a neutral salt and water. So you take these two things that are super caustic on their own, and when you combine them together, though, they become harmless. which is one of the neater things I think about chemistry. This is fairly common. Where you can have a chemical reaction between two very dangerous things that results in something very non-hazardous, or likewise you can have two non-hazardous chemicals that combine to form something that is very hazardous. So chemistry you always have to do carefully. But going back to this reaction here, so I have it written out as an equation: hydrochloric acid, which is a strong acid when it's mixed with sodium hydroxide, which is a strong base. It's a double displacement reaction. A neutralization reaction is a type of double displacement, so they swap partners. So the Cl and the Na get together and form NaCl, sodium chloride, which is our regular old table salt, and the H and the OH get together to form H2O, water. So these are totally non-toxic products. So when we say that it forms a salt and water, remember salt in chemistry is any ionic compound. Now, literally in our kitchen, salt is sodium chloride. And sodium chloride is certainly a very commonly used example salt in chemistry, but just want you to remember that salt does not necessarily mean sodium chloride. It's any ionic compound. A salt is any ionic compound. So when these neutralization reactions happen, they tend to be very exothermic, and that's because the combining of hydrogen and hydroxide, or hydronium and hydroxide, to form water is a very exothermic reaction. It produces a lot of heat. So if you're ever working with acids and bases in a lab, especially if they're strong acids, and you're adding them together, you always want to add acid to water. You never want to add water directly to acid because it will react, and if it produces too much heat too quickly, it will actually sort of explode. And one of the acids that does this is sulfuric acid. Is a very strong acid, and I've heard stories of people who were they had used like a beaker to put the acid in, and then they poured all of it out, and they went to go wash the beaker in the sink, and there was just a little bit of acid left in the beaker, and when they turned on the water full flow, it like splashed, because the exothermic reaction happened so quickly that it got hot and it sort of boiled over and splashed them in the face, and they actually sustained chemical burns from that. So very careful working with strong acids in the lab. Okay, sample problem here. We're going to complete and balance the following neutralization reactions. So we do have to predict what the products are going to be here. But we can do that because we know that the products of a neutralization reaction are always a salt, some ionic compound, and water. So the other thing that we know about neutralization reactions is that they are double displacement reactions. So what we're doing is we're just swapping partners. We're taking the cations and swapping them. So double displacement, I'm just going to write double dis. Okay, so we've got, in this problem, we've got HNO3, which is nitric acid, and KOH, which is potassium hydroxide. So if we sort of divided these into the ions, we have H plus and nitrate ion, a polyatomic ion, and here we have potassium ion, and potassium ion has a 1 plus charge because it's in group 1 of the periodic table, and all group 1 elements have 1 plus charge, and hydroxide is on that list of polyatomic ions, so it has a -1 charge. So now we're just swapping partners. So now the nitrate here, or sorry, well, let's start with the hydrogen. So the hydrogen is going to pair with the anion of the other molecule. So the hydrogen is now going to get together with the hydroxide, and that makes water, H2O. And the salt is going to come from the potassium and the nitrate getting together. we always write the cation first. So this will be KNO3. And that's because potassium has a 1 plus charge, nitrate has a 1 minus charge, so they combine in a 1-to-1 ratio. So we end up with potassium nitrate and water. We look at all the numbers here. There's 2 hydrogens, 1 potassium, 1 potassium, 1 nitrogen. So these are balanced as is. All of the elements are in equal numbers on both sides of the equation. I suppose the only other thing I should write here is that this salt is aqueous, it's dissolved in water, and that this water is a liquid. So I could put the states there. I won't hold you to writing states though. All right, next one, we've got HBr and CaOH2. Hydrogen bromide and calcium hydroxide. So again, we need to do a double displacement reaction. We know we're going to make water and a salt. So I'm going to do the same thing. I'm going to divide these into the ions. So hydrogen has a 1 plus charge, and bromine has a 1 minus charge. And calcium on the periodic table is in group 2, so it has a 2 plus charge as an ion. And hydroxide is a polyatomic ion that has a -1 charge. So we're going to combine the H, the proton, and the hydroxide to make water, H2O. And we'll combine the bromine and the calcium to make a salt. Calcium is our cation, so we write it first. Calcium bromide. Now calcium has a 2 plus charge, and bromine has a 1 minus charge. So when we combine them, we need to have 2 bromines to cancel out the charge on the calcium. So the ionic compound that forms between these two is calcium bromide, CaBr2. So if you need to review this concept of forming ionic compounds correctly, that was chapter 3 that you might want to review. So these are our 2 products. So now we've written the products out, but we do need to balance this equation because, let's see, over here I've got 2 bromines on the product side and only 1 bromine on the reactant side. So I'm going to need to add a coefficient here. So now I have 2 bromines and I have 2 hydrogens plus 2 hydrogens makes 4 hydrogens on this side of the equation. Here, I'll make my table. We'll do it this way. We're going to balance this one. A little shortcut for balancing is you can treat polyatomic ions. Nah, that won't work well. All right, take it back. Okay, so these are our different elements that we've got. Hydrogen, bromine, calcium, and oxygen. On the left side, before I put that 2 there, I started with 1 hydrogen, and I got 2 hydrogens on the product side. Bromine, before I put that 2 there, I had a 1. So I'm just going to tally up all of these starting amounts. I have 2 oxygens because there's a 2 outside the parentheses there, and over here I only have 1 oxygen. All right, and then I started by adding a 2 to give me 2 bromines, which also gave me 2 hydrogens. Oh, oops, I'd miscounted these. I didn't have 1 to begin with. I had 3 because I had 1 hydrogen here and I have 2 hydrogens here. So 1 plus 2 is 3. But when I put that 2 here, now I have 2 plus 2 makes 4. All right, so now I need to have 4 hydrogens on the flip side. So if I put a 2 here, then I've got 4 hydrogens, but I've also doubled the oxygens, so now I have 2 oxygens. And now I have balanced this equation. So I just needed to add a couple of coefficients of 2. So you might be asked on a test to complete and balance a neutralization reaction. So you need to know that a neutralization reaction is double displacement. So you need to be able to swap those cation-anion pairs, and end up with a salt and water as your products. So these neutralization reactions happen when we have heartburn and we take antacids. So antacids are actually just weak bases that you consume to neutralize the strong acid in your stomach. We wouldn't want to swallow a strong base because that would actually damage the esophagus. I don't recommend swallowing Drano if you have heartburn, but taking a Tums or some Maalox can be very soothing because they contain weak bases like aluminum hydroxide, magnesium hydroxide, or calcium carbonate, all of which react with acids and neutralize them in the stomach. They all also have various side effects, and knowing those side effects can help you pick the correct antacid for yourself. So ones that contain aluminum hydroxide has the side effect of being of constipation. So if you are someone who already struggles with constipation, you probably would not want to take an antacid that contained aluminum hydroxide. Magnesium hydroxide is a laxative. It increases bowel movement, so it kind of has the opposite effect. So that one, if you had constipation and heartburn, you'd want to go with a magnesium hydroxide containing antacid. A lot of antacids contain a combination of the two because that sort of helps to counteract their side effects. So one causes constipation, the other is a laxative, so they kind of cancel each other out. So you'll notice a lot of brands that have a combination of the two, and the reason being that their side effects cancel each other out, but they both work equally as well as antacids. Another common one is calcium carbonate. That's the main ingredient in Tums. And calcium carbonate, when it reacts with acid, produces carbon dioxide. And carbon dioxide is a gas, so it's very common to burp after taking a Tums because you produce that gas in the stomach. And that's just a side effect of those. Another thing is that they contain calcium. A lot of people actually take Tums as a calcium supplement. It can double as a calcium supplement because it contains calcium as a component. And then Alka-Seltzer usually contains sodium carbonate or sodium bicarbonate, which is basically just baking soda in water. So you can actually make your own Alka-Seltzer, and some people will do that. They'll put baking soda in water and drink that as an antacid. You do have to be careful though, because that sodium concentration can be a bit high, and if you have high blood sodium levels, that would be an antacid you would want to stay away from. So all of those things, like if some patient comes in and says, I have heartburn, and a doctor recommends an antacid, they may need to be aware of other health conditions that the patient has in order to recommend the correct antacid. So there's chemistry involved, but there's also some pharmacology involved as well. So since most acids and bases are weak acids and bases, and the reaction is reversible, they only partially dissociate, and they have this two-way arrow. This two-way arrow is called an equilibrium arrow. So an equilibrium, chemical equilibrium, this is the definition of chemical equilibrium, and you should commit it to memory, all right? It is when the rate of the forward reaction is equal to the rate of the reverse reaction. So the rate at which you are making product is the same rate as you are making reactant going in reverse. That is chemical equilibrium. It doesn't mean that you have the same amount of reactant as you do product. It has nothing to do with the amounts of each. It has everything to do with the rates. So rate being a key word in this definition. The forward rate equals the reverse rate. So I tried to make this little animation here. So in a chemical reaction, generally, you start with reactants. You have no products at the start. So at time 0 here, we have some concentration of reactants and we have 0 concentration of products. the reaction starts to go and the amount of reactants starts to decrease while the amount of products increases, right? And then sometimes that will go in reverse, and you end up at some point sort of the reaction stalls or it stops. It looks like it stops anyway because you're no longer making more reactants or products. You now have a steady amount of reactants and a steady amount of products. They're not equal. I have more reactants than I do products, okay? Same thing in this graph here. So as the reaction went on, the amount of reactant decreased and the amount of product increased, all right? But at some point they steady out and they're no longer changing. That is equilibrium. So at equilibrium, there's no longer a change in the amount of reactants or products, and that is because the amount of reactants that are turning to products is equal to the amount of products that are turning to reactants. It looks static. It looks like nothing's changing anymore, but in fact, it's a dynamic process. This reaction is still going, but it's going in both directions at the same rate, so you're not seeing a change in concentrations. It's a little confusing to think about. The graph is a good visual, but this video is also a good visual. And I might fast forward through parts of it.
All right, so what I'd like to do, just real quick before we move on to some new stuff, is I would like to give you just a quick demonstration, a way to sort of visualize equilibrium, okay? So what we're going to do is we're going to, I have a couple of plastic containers here. You should, what I'd like you to do is envision these together, right? They fit inside each other. This is our reaction vessel. This is where our reaction is taking place, okay? Where we have some chemicals, you know, A plus B going to C plus D. We have some generic chemical reaction, you know, right? We have A plus B going to C plus D. But remember, we're now talking about reactions that are reversible, so we can also have C and D go to reform A and B. So what I'm going to do is I want you to imagine sort of envisioning in your head that these two buckets, remember, are together in the same, they represent the same volume, the same container, okay? One of them is going to hold our reactants, and one of them is going to hold our products. And we're going to have reaction rates, okay? The rate of the chemical reactions are represented by the size of the beaker. The bigger the beaker, the bigger the potential forward rate. These beakers represent essentially the rate constants. Okay, these are the rate constants. The reverse reaction has a smaller rate constant because this is an exothermic reaction. So under these conditions, it's harder for the reverse reaction to take place. Okay, so the rate constant is smaller. This is our forward reaction, larger. It's a bigger beaker, a faster potential reaction. Okay, so the reactants are just going to be some water. Start off with about 1 liter of water in here. And that's really hard for us to see, so we're just going to add some food coloring to it. Okay, so now it's pretty easy to see the levels, right? We can see the level of the water. Okay, remember, these are in this, they represent the same physical volume. It's just so we can separate out the reactants and the products. Now we're going to imagine this reaction taking place in tiny slices of time. Okay, so over a tiny piece of time, we scoop from both sides, okay? Now, remember the size of the beaker represents essentially the rate constant K. How much liquid do I have in the forward reaction? I have a full amount, right? I have a lot. This reaction is happening very quickly. And the reverse reaction has, why? There are no products yet. So there's nothing for the reverse reaction to take place with. So I'm going to scoop them over. Okay, this pouring represented reactants turning into products and products turning into reactants. The two parts of this reaction, the forward and the reverse. Okay, now you can see the concentration of the products has increased. So when I scoop this time, okay, I'm getting some products changing into reactants. Notice what happened to the amount in this beaker. Did it go up or down? It went down. Why would it go down? The concentration of my reactants is decreasing, so the rate is decreasing. So I pour, the rate of the forward reaction is decreasing, while the rate of the reverse reaction is increasing. Okay, so again, notice the reverse reaction is speeding up. It's getting fuller and fuller beaker. This one is continuing to go down a little bit. It's going down slowly. Okay, notice again, the forward reaction is starting to drop. The reverse reaction rate continues to speed up. But what's going to happen is that we're going to get to a point after we let this reaction go for a little bit where these two beakers essentially are holding the same volume. So we look at the concentrations here. Hold on just a second. Let me get some so you can see this. So the height of the liquid inside here represents the concentration. The more stuff in the beaker, the greater the concentration, because remember, these are in the same physical volume. So the concentration of the products has increased. The concentration of the reactants has decreased. If I look at my forward reaction, remember this beaker represents my forward reaction rate. If I look at the amount of, then I do this, remember this little beaker represents the reverse reaction rate. Okay, they are starting to get closer together. So we're going to scoop again. Now let's measure. Okay, so you can see that those two levels are about the same. Okay, we're going to call this essentially at equilibrium. Okay, now I can pour these over, and I can continue to do this. I can continue to have this reaction take place. This is what happens in an equilibrium, right? I continue to dump. And again, to within the error of my measurement, those are basically the same level. My scooping isn't perfect. This is a simulation, right? And I can keep pouring as long as I want. They're going to continue to be at the same level because the rate at which I'm transferring from one to the other is the same. Okay, when I scoop from here and I scoop from here, I'm scooping the same amount. The forward and the reverse reaction rates are the same. Are the height of this water, are the concentrations of these products and reactants equal? No. Are they changing anymore? Nope. The rates are equal, the concentrations are steady. Okay?
So I love that demonstration. It's really clear. You can see, kind of visualize those equal rates when he pours it into those graduated cylinders. You can also see really clearly that the amount of reactant and product are not the same at equilibrium. They are different volumes or different concentrations, but they are staying the same. They're not changing, and that's another sign of equilibrium. So we can calculate the equilibrium constant for a reaction, which kind of is a number that tells us what that ratio of reactants to products is going to be at equilibrium. Which will there be more of? Will there be more product or more reactant? And so we call this the equilibrium constant, and we give it the name, or the letter K is what represents it. It's a capital K. Okay, so K is a ratio of the concentration of products at equilibrium to the concentration of reactants at equilibrium. Brackets in chemistry mean concentration of. So for any given reaction, let's say we have A plus B reacts to form C plus D, where the lowercase letters represent any coefficient in front of that chemical. All right, then the formula to calculate the equilibrium constant would be the concentration of C to the C power times the concentration of D to the D power over the concentration of A to whatever coefficient it has, and times the concentration of B to its coefficient. So this is the basic setup. This is how we would set up an equilibrium constant expression, is what we call this. So another important thing to note is that the only thing that goes into this equilibrium constant expression are things that are in the gaseous or aqueous state. And that's because only gases and solutions have concentrations. All right, a solid doesn't have a concentration. The wood on your table and chairs doesn't have a concentration. And pure liquids like water doesn't have a concentration. If you dissolve something in water and make an aqueous solution, then we can talk about the concentration, but pure liquids and solids don't have a concentration. So anything in the equation that's a liquid or a solid just gets excluded from this equation here. So let's do some examples. This is a worked example here. So here's the equation to make ammonia from gaseous nitrogen and gaseous hydrogen. So we've got N2 plus 3H2 reacts to form 2NH3. So the equilibrium constant expression would be K equals the concentration of the product, NH3, to the power of that coefficient 2, divided by the concentration of N2, there's no coefficient there, so there's no power, times the concentration of the other reactant, H2, raised to the power of 3 because of that coefficient 3 there. So let's practice writing equilibrium constant expressions for the following reactions. All right, so the equilibrium constant expression is going to start with K equals. And it's going to be the concentration of the products over the concentration of the reactants. So first, I'm going to do products on top. So I've got CO and H2. All right, I don't put the coefficient in the brackets. It's not 3H2, it's just H2. I'm just writing the formulas in the brackets. And that 3, the coefficient, becomes the superscript here, the power. So CO, carbon monoxide, that is one substance. I'm not going to break it up into carbon and oxygen. I keep my substances, the compounds, together, right? The only thing I split apart is I separate that coefficient and I move it to be a power, all right? Both of these are gases. I probably should have checked that first before putting my equation together. Everything here is a gas. So I'm going to include all of these in my equilibrium constant expression. On the bottom of the equation, I'm going to put the reactants, which are CH4, which is methane, and H2O, which is steam in this case because it's gaseous. H2O, neither of which have a coefficient, so neither of those get raised to any power. So that's all you have to do an equilibrium constant expression. I'm not actually even giving you any math to calculate what the value of K is. You're just setting up the expression based on the equation. Now for part B, let's go look at the units for part B. So part B, calcium carbonate is a solid. So this is not going to go into our equilibrium constant expression. The gas will, but the solids will not. So the equilibrium constant expression for this one is the concentration of products over the concentration of reactants. The products, the only product that we're putting in here is carbon dioxide. And there's no coefficient, so there's no exponent here. And in the reactants, none of the reactants are going in this equation because the reactant is a solid. So we can put a 1 as a placeholder there. Or we could just say K equals. We can just get rid of that denominator altogether and say K equals the concentration of CO2, period. All right, so the things you need to know for equilibrium constant expression, you need to know how to set up the equilibrium constant expression, that it's the products over the reactants, not the other way around. You need to know how to make the coefficient into an exponent, And you need to know not to include things that are in the solid or liquid state, only things in the gaseous and aqueous state. You also should know what the value of K means. So if K is equal to 1, that means that the concentration of the reactants and the products at equilibrium are equal. The numerator and the denominator are the same, then K will equal 1. So K of equal to 1 is pretty rare. Most reactions don't stop halfway in the middle like this where there's an equal number of each. More likely, the value of K will be either less than 1 or greater than 1. If it's less than 1, it's because the denominator is larger than the numerator, meaning that there are more reactants at equilibrium than there are products. And so a K of less than 1 means that reactants predominate at equilibrium. And if the K is greater than 1, it means that the products predominate, that this numerator is larger than the denominator, so there's more products than there are reactants. A good question would be, in that previous demonstration that we watched, would that reaction have a value of K that was equal to 1, less than 1, or greater than 1? Did it have more products at equilibrium, or did it have more reactants? All right, let's do this sample problem. K for the following reaction at 25 degrees Celsius is 1 times 10 to the second power. Based on the value for K at equilibrium, are the products or the reactants greater? So 1 times 10 to the 2 is scientific notation for 100. Is 100 greater than or less than or equal to 1? Well, in this case, K is greater than 1. It's 100. So in other words, at equilibrium, the concentration of the products over the concentration of the reactants is equal to 100 over 1. Is literally what that number means. All right, if it's equal to 100, we could also write that as 100 over 1. So that means that the products predominate at equilibrium. There's more products, 100 times more products than there are reactants at equilibrium. So any number greater than 1 is going to tell us that products predominate. And you could have a series of questions that are worded similarly to this, asking you, based on the K value for some reaction, which is going to predominate. So this one says, will the products or the reactants be greater? But it might say which one will be greater concentration, the carbon monoxide or the carbon dioxide. All right, and in that case, you should be able to say the carbon dioxide because, again, we know the products are greater, and carbon dioxide is a product, carbon monoxide is a reactant. So there's different ways these questions could be worded. Another thing it could say is which reaction is favored, the forward reaction or the reverse reaction. So if there's more product, that means that the forward reaction is favored, that the forward reaction makes more product than the reverse reaction. Alrighty, so when it comes to equilibrium, equilibrium will be achieved if you, like in that demonstration, if you just keep going, reactions will always go towards equilibrium. They'll always sort of spontaneously try to get to equilibrium and maintain equilibrium. But if that professor had added more water to one of those buckets, all right, that would have ruined the equilibrium, and it would continue going until it reestablished equilibrium, until it got back to equilibrium. And so the scientist who sort of figured this out, how you can mess up an equilibrium but still go back to equilibrium, was named Le Chatelier. So Le Chatelier's principle says that if you apply a stress to an equilibrium, if you take a reaction that's at equilibrium and you basically mess up the equilibrium, it will shift in order to get back to equilibrium. So all reactions are always kind of going and trying to get to equilibrium. So I like this sort of visual analogy that if you have a scale, all right, and the scale represents equal, when it's balanced, then the reaction's at equilibrium. All right, you can tip that scale, you can mess up that equilibrium by shifting it one way or the other, and it will shift in the opposite direction in order to get back to equilibrium. So for example, if that professor with the buckets of blue water had added more water to the product bucket, all right, then the reaction would have shifted to make more reactants to get back to equilibrium. So it would shift in that direction. So the sort of rules of Le Chatelier's principle is that A, the first one is, if one side gains a substance, it will shift in the other direction. So if you add reactant, it will shift right towards the product. If you add product, it'll shift left towards the reactant. So whichever thing you add, if you add something to one side, the reaction is going to shift to the other side. So that's rule number one. If you subtract, is another thing you can do. If you subtract reactant, you're going to shift toward that side in order to replace it. So if you lose a substance from one side, you're going to shift towards that side. If you take away product, you'll shift towards the product, all right, which would be shifting right. So there are different, so those are two ways to shift an equilibrium, to either add more of a substance or remove some of a substance would shift the equilibrium. A third way to shift an equilibrium is to change the temperature, right? And this makes a lot of sense if we think about one of the ways that we talked about exothermic and endothermic reactions is we visualized heat as either a product or a reactant. So for exothermic reactions, those are ones that produce heat, and we think of heat as being a product. And endothermic reactions are ones that absorb heat, so we would picture heat as being a reactant. And if we think of heat as a product or reactant in that context, we can use the first two rules basically. If we add something to one side, so if you add heat, you're going to shift it in the other direction. And if you subtract heat, you're going to shift it in that direction. So it's really kind of like just two rules to remember. If you add to one side, you shift to the other. If you subtract from one side, you shift toward that side. So in this case, if we were to increase the heat of this if we were to increase the temperature of this reaction, we would actually shift it towards the left. It would make more reactants. Whereas if we decrease the temperature, we remove heat, it would shift it towards the right and we'd be able to make more product. And this is really a useful tool for practical chemists who are trying to maybe make some kind of a product. If you're trying to generate ammonia, you're going to be able to generate more from these gases if you do it at a low temperature than if you do it at a higher temperature, says Le Chatelier's principle. So let's do a sample problem. How does each of the following actions affect the equilibrium of the following reaction? So we've got SO2 plus O2 becoming SO3 and also heat as a byproduct. So pop quiz for you, is this reaction endothermic or exothermic? Hopefully you said exothermic because heat is a product. All right, so the first thing it says, if we add O2, what is going to happen? O2 is a reactant. If we add something to the reactant side, we're going to shift it towards the product side. So in this case, we would say it would shift right, or it would shift towards the products. If we lower the temperature, it's like we are removing heat. And when we remove something, we shift it in that direction. So if we remove a product, we're going to make more product. We're going to shift it to the right or towards the product. And then lastly, if we add SO3, SO3 is a product. If we add product, we're going to shift it in the opposite direction towards the reactants or to the left. So in a homework or on a test question, Any of those are appropriate responses. You could either draw an arrow to show me which way it's shifting, you could write a direction, left or right, or you could say towards reactants or towards products. So acids and bases, weak acids and bases, of course, equilibrium is relevant to them because they are at dynamic equilibrium. They are reversible reactions. And so when we talk about acids and bases, we give them a K value. For acids, we call it a Ka, and for bases, we call it a Kb, but it's just the equilibrium constant. It's just the concentration of products over the concentration of the reactants. And it basically just tells us how much of that acid dissociates. In other words, it also tells us how much hydrogen ion it's going to produce or hydronium ion it's going to produce. So if we were to write out the K, the equilibrium constant for this reaction, all right, anything aqueous goes, so check, check, check. Liquids do not though, so we would not put this in our equilibrium constant expression, but we would put this one. So the equilibrium constant expression for this equation would be the first compound, CH3COO minus. All right, substance number 1 times the second one, which is H3O plus. All right, so I'm not splitting anything up here. I'm just writing these. For some reason, a big mistake that students make is they, for some reason, decide to split these compounds up into different substances. Okay, but you don't want to do that. You want to keep the products as they're written. And then the only reactant that's going to go down here is the aqueous one, CH3COOH. This is acetic acid. It's a carboxylic acid. It's got a carboxylic acid functional group. And it is the main ingredient, or it is the acidic ingredient in vinegar. So the Ka, since it's the equilibrium constant, and the larger the K value, the more dissociation, the more product is formed. Because of that, the larger the Ka value of an acid, the stronger the acid is. In other words, the more product it forms, the more it dissociates. So the Ka values for weak acids are all pretty small. Notice the exponents in the negatives, so meaning they're all less than 1. All right, but so all of them will favor the reactants because they all have a K value of less than 1, but still some will produce more product than others. So the larger the Ka value is, the stronger the acid is. In fact, sometimes a question in the homework might just say, which of these two acids is stronger? Sorry, it's my phone. Go turn that off. I hope these interruptions are entertaining and not distracting. All right, so a simple homework problem might just ask you which one is the stronger acid, and it'll give you 2 acids and give you their Ka values and simply ask you to pick the one with the higher Ka value. So another way that we can measure the strength of acids is using a scale called the pH scale. And the pH scale is a measure of the amount of hydrogen ions that are in an aqueous solution. The more hydrogen ions there are, the more acidic the solution is, because remember, acids produce hydrogen ions. So pure water actually contains a mixture of hydrogen and hydroxide ions because of water's ability to auto-ionize, in other words, to ionize itself. So you have 2 water molecules, which are polar molecules. So the hydrogen is partially positively charged and the oxygen is partially negatively charged. Well, sometimes, like 1 in a million times, this partially negative oxygen, that electronegative oxygen, will actually pop off that hydrogen and you end up with a hydroxide ion and a hydronium ion. So in pure water, there are actually a small concentration of hydronium and hydroxide ions, but they're equal. They cancel each other out. So a way to visualize this, in a neutral solution of pure water, you actually have an equal amount of hydronium and hydroxide ions. So pure water is not neutral because there's no ions. It's neutral because there's an equal amount of both types of ion. An acidic solution is one that has more hydronium ions than hydroxide ions. And vice versa, a basic solution has more hydroxide ions than hydronium ions. So it's not purely one or the other, it's about the amounts. So the pH scale, if we look at the concentration of hydronium ions as it gets higher and higher here, so the concentration of hydronium ions are always going to be these very small numbers, so using these exponents. So like, let's say you have a solution where the concentration of hydronium ions is 2.6 times 10 to the negative fifth. So 2.6 times 10 to the negative fifth would be somewhere around here on this scale. All right, but those numbers like 2.6 times 10 to the negative fifth, that's just kind of like an unwieldy number that we don't like to work with numbers in scientific notation. We like to work with numbers between 1 and 10. That's a nice range to work with. And so the pH scale is basically just a log scale where we convert the concentration of the hydrogen ions into an easier number to work with by taking the negative log of it. So you'll notice that if the concentration of hydronium ions or hydrogen ions is 10 to the negative fifth, that's a pH of 5. If it's 10 to the negative 8, that's a pH of 8. All right, so you can see how these scales line up. So I'm not going to make you guys do the math to calculate the exact pH, but you should be able to estimate the pH just by looking at that exponent. So in this case, if the hydronium ion concentration is 2.6 times 10 to the negative fifth, that is a pH of about 5. Would that be acidic or basic? Well, anything below 7 is acidic. Any pH below 7 is an acid. Above 7 is basic. Hence the meme, she's a 10, maybe on the pH scale, because she basic. I can't do it from memory. Okay, so this one here, the second one, 4.4 times 10 to the negative 11. That negative 11 tells us that the pH is going to be about 11. Right? pHs are pretty much always positive. Very, very, very strong acids can have a negative pH, but most of the time everything's going to be in the positive range. Okay, so a pH of 11, which would be basic because it is greater than 7. So you do not need to know how to do the negative log in your calculator. You just need to be able to estimate the pH. So in any homework problems that I give you, like from the textbook, I would just want you to estimate it. I'm going to try to find ones online where it'll be exact. So where this number is 1.0 times 10 to the whatever, because then the estimate will be the exact pH. So pH can be measured using a pH meter, which is a machine that can measure the hydrogen ion concentration and give you a more exact number. There's also a lot of plant dyes that change color at different pHs, and they can be put onto strips of paper that you can make these test strips where you can test pH just by touching the piece of paper to the solution and then comparing it to the colors in a key to determine the pH. And this is a little bit less exact than using a pH meter, but still useful. So let's do this practice problem here. State whether the solutions in the following conditions are acidic, neutral, or basic. So we need to know the pH. So A, it tells us straight up the pH is 5. pH of 5 is less than 7, so that's an acid. We'll do C too. C is a pH of 12, that's greater than 7, so that's a base. Those two are easy because it gives us the pH. B, D, and E give us a hydronium ion concentration, so we have to figure out or estimate what the pH is going to be. This one has an exponent, so it's times 10 to the negative ninth, so that's going to be a pH of about 9, and that is basic, greater than 7. Part D, 4.3 times 10 to the negative 4, that's going to be a pH of about 4. And that would be acidic because it's less than 7. And then lastly, we've got one that's 1 times 10 to the negative 7th. That's going to be actually equal to, it's because that's a 1, that's going to be equal to a pH of 7, but we can estimate it at 7. And a pH of 7 is neutral. So remember with Bronsted-Lowry acids and bases, they said that an acid is a proton donor and a base is a proton acceptor. And so that means that they kind of happen together, that acid-base reactions happen just like redox reactions. One is a donor, the other's the acceptor. And so we can, I don't know what I wanted to say. So we can take the acid and the product of the acid and call it the conjugate base. So we call this a conjugate acid-base pair. I'm not explaining this well. So the acid, after it donates its proton, all right, it becomes a molecule that in the reverse reaction acts as a proton acceptor or a base. So if we look at these weak acids and weak bases that are in these reversible reactions, the thing that acts as the acid in the forward reaction ends up being the base in the reverse reaction. So we call these things conjugate acid-base pairs because they can work as an acid and a base. So whichever is the acid in the forward reaction becomes the conjugate base in the reverse reaction, and whichever substance is the base in the forward reaction becomes the conjugate acid in the reverse reaction. In other words, whichever thing is accepting the proton in the forward reaction is going to give up the proton in the reverse reaction. So conjugate acid-base pairs are identical compounds that differ by an H+. So CH3COOH and CH3COO- are a conjugate acid-base pair. This is the one that acts as the acid that has a proton it can give up, and this is the one that acts as the base. It can receive a proton. And same thing with water and hydronium, H2O being the base and H3O+ being the conjugate acid. So conjugate acid and base pairs can be really useful in creating buffers. And a buffer is something that resists pH change. It's a solution that can resist a change in pH even if you add acid or base. And that's because it contains equal amounts of acid and base such that when you add an acid, the base neutralizes it, and when you add a base, the acid neutralizes it. But the acid and base together kind of balance out that solution. So buffers are neat because if you have water, if you have a beaker of water and you add just a single drop of acid to it, like a strong acid, like hydrochloric acid, the pH will drop a lot, like significantly. Like it'll go from neutral 7 down to like 2 from that one drop of concentrated acid. So pure water can undergo very extreme pH changes just by adding a little bit of acid. Whereas if you had a buffered solution that had a pH of 7 and you add a drop of acid, the pH doesn't change, or it might change to 6.95. It'll change very little. You have to add a lot of acid for it to actually go down to 2. And this is important biologically because pH is really important in the environment of our cells. Our cells can't really withstand drastic changes in pH all the time. And so if a little bit of acid enters the system, you don't want it drastically changing the pH of your cells. And so buffers. We have buffers in our blood to help neutralize any acid or base that builds up so that our pH can stay the same. And the pH in our body is roughly neutral. It's about 7.3, 7.4. And we really need to keep it at that, or otherwise bad stuff starts happening. So that is a buffer. So an important buffer system in our blood is the bicarbonate buffer system, and it helps us to neutralize the acid that's formed from carbon dioxide and water in the blood. So at the very first slide, I talked about soda and how carbon dioxide, when dissolved in water, forms carbonic acid, and carbonic acid is an acid, and so it would react with water to form hydronium ions. So when you breathe oxygen and it goes to your cells metabolize it, they use the oxygen to make ATP. And a byproduct of that is carbon dioxide, which goes back into the blood to go to the lungs so you can breathe it out. Well, that carbon dioxide in your blood does actually acidify the blood a little bit. Carbon dioxide dissolved in the blood, which contains a lot of water, will turn into carbonic acid, and the carbonic acid will dissociate, partially dissociate, into hydrogen ions. And that raises the pH of the blood, because that's what pH is. It's an increase in hydrogen ions. All right, so what can happen is that if you have too much carbon dioxide, you end up raising the amount of hydrogen ions in the blood. If you have too little carbon dioxide, you can reduce that. And just by the influx of air into and out of your lungs. So we're going to talk about respiratory acidosis and respiratory alkalosis. So in respiratory acidosis, you're increasing the amount of carbon dioxide in the blood, and that increases the amount of carbonic acid and the amount of hydrogen ions. This can happen in people with hypoventilation, so people who can't exhale fully due to things like COPD and emphysema. So chronic damage to the lungs can impair the ability to exhale proper amounts of carbon dioxide. And so what happens is they end up building up amounts of acid in the blood, and that causes acidosis or acidification of the blood. And that can lead to bad things. The opposite scenario, hyperventilation, right? When somebody's hyperventilating, I don't know if you've ever hyperventilated, I have had a few panic attacks in my experience. Not fun, but you tend to breathe like this. So your intake of air is like you're not breathing in fully, but you're breathing out fully. And so you're breathing out plenty of carbon dioxide. And so some people think, so you start to get lightheaded, and it's not actually because you're not getting enough oxygen. Your cells have plenty of oxygen still. Even with your like sort of wheezing intakes, because it's temporary. It's the fact that you're breathing out a lot of carbon dioxide that is the problem. And so one of the stereotypical remedies for someone who's hyperventilating is to give them a bag to breathe into so they can breathe back in some of that carbon dioxide. Because what's happening, the reason they get lightheaded, is because they're breathing out a lot of carbon dioxide and they're shifting that equilibrium. So this is all the Chatelier's principle here. They're reducing the amount of carbon dioxide, and that's going to then reduce the amount of hydronium ions. So if you're reducing the acid, you're making it more basic. And another term for base is alkaline. So respiratory alkalosis is when the blood is becoming more alkaline, more basic. And that's actually what gives you that lightheaded effect, that respiratory alkalosis. So the acidification or basification, alkalinization of the blood that occurs under these different respiratory conditions has everything to do with acid-base chemistry and equilibrium and Le Chatelier's principle all put together. So these are some other forms. This is just a table from the book looking at some of the symptoms of these different forms of acidosis and alkalosis. So we just talked about respiratory acidosis and alkalosis. Another one is metabolic acidosis and alkalosis. So for example, somebody who has who's been vomiting a lot, or has really bad diarrhea, but mostly if they're excessive vomiting and they're getting rid of all that stomach acid, all right, they're getting rid of acid. That means they're reducing the acid, they're becoming more basic. All right, so that's metabolic alkalosis, and that can happen to somebody who has excessive vomiting, in addition to the fact that they can also become dehydrated. So that's why sometimes people need to be hospitalized from lots of vomiting, because it can mess with their blood chemistry. So yeah, I won't test you on these different symptoms and whatnot, but it is sometimes fun to read about. All right. That is the end of this lecture, and I know it's been kind of a long one, but I can't leave you without playing this wonderful acid-base song for you.
Because you know I'm all about that bass, no acid. I'm all about that bass, no acid. I'm all about that bass, no acid. I'm all about that bass, bass. Yeah, it's pretty clear, I ain't no science fool. So you got litmus, well I can turn it blue. Make it go boom boom all over the place. When all the H plus meet all the OHs. Pink phenolphthalein, I think that's straight dope. Mix in a lipid here and it'll make it soap. You want it neutral, pH is low. Better set up a titration with a strong hydroxyl drop. Yeah, my lab tech, she told me don't worry about your eyes. If an acid gets in them, we just have to neutralize. You know I love me, my stomach, and all the things it dissolves. But my powder keeps it from eating my intestine walls. Because you know I'm all about that bass, no acid. I'm all about that bass, no acid. I'm all about that bass, no acid. I'm all about that bass, Ha!